All right, I'm about to do the wave review. I've already solved every problem, and I'm going to go pretty fast. Otherwise, this is going to be a ridiculously long video if I explain every little intricacy. I'm not going to read the problems because I assume you have the sheet in front of you, and you can then go look at, say, you have trouble with number 3. You should be able to scan through until I'm pointing at each problem and figure out where you need to stop and listen to my brief explanation of each of the 45 questions. Given that this was a test that sort of combines 2 units, this was a fairly lengthy review, but the questions on it are simpler than we faced on like our Newton's law test, etc. So, starting with number 1, we have a pendulum. We have a length of 0.369. Some of you might forget to convert that to meters, period. Our formula, period, is equal to 2 pi times the square root of L over G. Plug and chug, and we get gravity to be 9.787. If you're not getting the right answer, it's probably because you're forgetting that when you divide by 2 pi in your calculator, you need to put parentheses around the 2 and the pi. Question 2, what controls the velocity? Medium controls the velocity. Frequency is controlled by the source, and remember that it doesn't change after being created. And then lastly, the amplitude. The source also controls that, although it does die off over time. Number 3, if we double the velocity of a wave, the wavelength will also double because v equals f lambda, and frequency has to stay the same. So if velocity goes up, frequency also has to go up. On number 4, the words you're looking for are nodes and antinodes. That's total destructive and total constructive. We see that in interference patterns. Number 5, we have waves that are 6 meters long, traveling 5.6. We're supposed to find the frequency and the period. V equals f lambda, so 5.6 equals frequency times 6. The frequency is 0.93. And then I just hit x to the minus 1 in my calculator, and I get the period of 1.07 because period is 1 over the frequency. Next, number 6, it describes a situation where we have a long-standing wave, and the distance between the third and the 6th node is 54 centimeters. I know the distance between each node is a half a wavelength, therefore this is 1.5 waves, and it equals 54. Therefore my wavelength is 36 centimeters or 0.36 meters. I'm given the frequency of 10 and my wavelength of 0.36, and I get a velocity of 3.6 meters per second. All right, up to the top here. Number 7. How does a single point on a string move as a wave travels by? If it's a transverse wave, the wave is going this way. The particles go in and out, such as our Slinky lab. Number 8. Why do we use electromagnetic waves for signals? Why does it work for your cell phone? Because they're really fast. You now know the speed of light is 3 times 10 to the 8th. All electromagnetic waves travel that fast, and they don't require a medium, and they're often not affected by the medium, although light will slow down in different things like glass and plastic and water, and we'll learn about that in refraction. Number 9. What's common to all waves? This is a really broad question, just kind of asking you to examine waves in general. They're all transfers of energy with very little particle motion. They can refract, they can diffract, they can go through interference, they require mediums, they have frequencies, all that good stuff that you know about waves. Number 10, can 2 or more waves interfere in a given medium? Of course they can. If I have sounds in a city, they can all travel through each other. Light from a bunch of light sources in a room or a stadium filled with sound. Number 11, we're looking at fixed end and free end. In a fixed, it changes phase and bounces to the opposite side. In a free end, it hits and bounces back on the same side to us, so it does not change phase. Number 12, you dip your finger in water twice each second. That's 2 cycles per second. That's our frequency. That means our period is 1 over 2. That's our period. It takes 2 seconds or 2 waves per second. That means it's a half a second per wave. We're told that the wavelength is 0.15, so our velocity must be 0.3 meters per second. 13, harmonic wave traveling along a rope. We get 40 cycles in 30 seconds, or 4/3 of a hertz. Velocity is 4.25 meters per 10 seconds, or 0.425 meters per second. Notice I converted that from centimeters. And then velocity is frequency times wavelength, so 4.425 meters per second. divided by 4/3 hertz equals 0.319 meters. So there's number 13. On to number 14. We have a variety of things that kind of relate to our wave tanks. 14 is about diffraction. Waves travel through an opening and they spread out. If I have a door that's closed, it might diffract under the door and spread out. We know that low frequency waves do this more, so bass would travel more through a building. When they travel past an opening, they tend to bend, so they would go around a corner and bend down a hallway. So those low frequency sounds travel really, really well. Number 15 is supposed to bounce waves off a parabolic reflector. You can see straight waves coming in straight. They bounce, they all go through a focal point and then back out in an arc as if they had originated from that point, sort of a circular wave. 16, they bounce in this way, they bounce out at whatever angle they came in at. That's the law of reflection. We've now learned that in light. So whatever angle you come in at, you also come out at. Number 17. I'm supposed to actually measure some things on this. So I measured the distance between the crests on this right here. We can see that's 4 centimeters. That's 8. Those are the numbers that I used. I forgot to measure the amplitude, but the amplitude is from here to here, or I could measure from here to here and divide by 2. It ends up being 1 centimeter there. So coming back, my velocity is 8 centimeters in 2 seconds, or 0.04 meters per second. Plugging that in, I get 0.04 meters per second is equal to frequency divided by 0.04, and I get 1 hertz. So that's the answer to 17. 18. We are given a temperature of 20. We plug that into 331 plus 0.6 times 20. We get the velocity of 343. That equals distance over time. Time is 3.4 seconds, so I know it travels 1166.2 meters. But it's an echo, so it goes out and back in that amount of time. So I know this must be 583 meters to get to the wall, 583 meters back. Next problem, it gives a speed of sound of 350. So we plug that into 331 plus 0.6 T. We get T to be 31.7 degrees Celsius. Number 20, we're making our way. We're about through the first page here. Number 20, we have temperature of 20 degrees. So we plug it in, 331 plus 0.6 times T, we get 343. And then I know that it travels for 5 seconds, so 343 meters per second times 5 seconds. That's VT equals X, or velocity is distance over time. I get 1715 meters, which is a little over a mile. Number 21, we are given 2 different mediums for sound to travel in. Those 2 mediums are steel, 50/50 is the number I gave my class, and air with 25 degrees. So we figure out our speeds. We plug them into distance over time. We have 3,500 meters to travel. And 3.5 kilometers is 3,500 meters. In the steel, it takes 0.69 seconds to travel that far. In air, 3,500 meters takes considerably longer at 346 meters per second and 10.12. And then I simply subtract it. I get a 9.42 second differential between the steel and the air. Number 22. Number 22 is definitely the hardest problem on this review. If you got through it, well done. I'll explain it in a little bit greater detail here. What we did is we dropped a rock down a well, and it falls accelerating all the way to the ground, to the water, and then it makes a splash, and that sound shoots back up the well at the speed of sound. So the speed of sound, we know it travels 340 meters per second, and that equals X, the depth of the well, divided by the sound time. We don't know what the sound time is. The rock travels distance X with an initial velocity of 0 at 1/2 gravity times time squared. So we end up with 1/2 times 4.9, 1/2 of 9.8, time for the rock squared, but we don't know that either. But we do know that the time for the sound plus the time for the rock equals 3 seconds. Okay, so now I have 1, 2, 3 equations. At this point, I started setting things equal to each other. I solved this equation for X, And I knew this equation was already equal to x. So I said that 340 times the time for sound equals 4.9 times the time for the rock squared. Then I have two unknowns. I have time for sound and time for rock. I can't have that. So I'm going to replace time for sound with 3 minus time for the rock. What I did is I just moved that over there. I distribute the 340 through. I get this. That equals 4.9 time for the rock squared. And then I move it into quadratic form. I plug it into the quadratic solver, and I find the time for the rock is 2.88 seconds to fall. I then plug this back in up here, and I get 40.64 meters. Now, don't think that I'm going to make you do that on a test. But if I gave you the depth of a well, could you find it? Then we're not doing multiple equations, multiple unknowns. Just an example of some things that we might have to do. It's more like an echo problem at that point. On to number 23. I'm on to the second page, and so far this has taken 11 minutes, so we're doing okay. Number 23, we have a bat flying towards a wall and then hearing his own echo. So if he's flying towards a wall, he's already creating a Doppler shift to go a little bit higher. And then as it's coming back off the wall, he's flying through the sound that he created, so it ends up Doppler shifting twice because it Doppler shifts in front of him and then Doppler shifts as he's flying through it. So it's higher because of two reasons. That doesn't mean it's twice as high. He's not going close to Mach 1 or anything like that, but he is hearing it shifted twice. How can we destroy things with sound, vibrations? The Tacoma Narrows Bridge was an example of this. We had wind that created a wave that traveled at a good fundamental frequency of the bridge. The waves built, and over time, they got so ferocious that they ripped the bridge apart. 25, the relationship between closed and open tubes. Closed tubes hold odd fourths of a wave. So we go up by odd fourths, 1/4, 3/4, 5/4. Open tubes, they go up even fourths. So we start at 0, then we go 2/4, 4/4, 6/4, which ends up being 1/2, 2/2, 3/2, 4/2. So we have 1, 3, 5, 7, 9 harmonics over here. We have 1, 2, 3, 4, 5 harmonics over here. Going on up as far as you want to go. Number 26, we have a person exceptionally sensitive to 3800 hertz sounds. Why is this? Well, our ear canal is a closed tube. If I do velocity is frequency times wavelength, I get 340 equals 3500 times wavelength. Then we get 0.089 meters for the wavelength. Since it's a closed tube, I then find a fourth of it, and I find 0.0223, or 2.3 centimeters, which is about how long the average ear canal is. And there's a little bit more that goes with the diameter. So just generalizing here, but that is part of the reason we're so sensitive to 3500 to 4000 hertz. And I wrote, somehow I wrote 3500 in here, but I believe I typed in 3800. I don't know. It's supposed to be 3800. I'll check that real quick. 340 divided by 3800, and I get 0.3894, which is what I wrote here, so I don't know why I wrote 3500 on there, but I did plug in 3800. Number 27. 27, we have I1 over I2 equals R2 squared over R1 squared. We're given that it's a 70 decibel sound, and 12 minus 7 gives me that 5. I can then plug it in as I1, 10 to the minus 5, over just to the point where we can't hear it anymore is 0 decibels, so that's 10 to the minus 12. I'm looking for where that happens. So R2 is what I'm looking for. R1 is 1. Solve for R2, and we get 3162 meters away. So if I am 3,162 meters away from a 70 decibel source, I will eventually get to a point where I cannot hear it. That's 3 kilometers. That's a pretty incredible distance. Number 28. I'm supposed to determine when an ambulance has passed me. As it's coming towards me, I'll hear it higher. As it goes away, I'll hear it lower. Therefore, I hear that Doppler shift, that meow, right? So Doppler shift tells us when it's passed. Number 29. You can go try this in your kitchen. Get a tall, narrow glass, run water into it, and you'll hear the water kind of go up as it shortens that air column in there. You can try it in the fridge filter or whatever you've got wherever you fill the water, and it makes a little sound as it fills the glass. Number 30 is a Doppler effect question. We have a fire station. Fire stations don't move, so in this case the observer's moving. 3,500 hertz is the frequency of the source. Velocity of sound, I used 340. And minus 11.1, because it's 40 kilometers per hour, is 11.1 meters per second. And this works out to be 3385 hertz. So we hear something slightly lower as we drive away from it. Why is it minus? Because we're going away. So this fraction needs to be less than 1. And if I'm altering the top, I have to subtract. As long as you know it's supposed to go down, you can do plus and minus and figure out which one's lower because you're moving away. Number 31. So back to where you can see that on the camera. 31, we're supposed to convert each one of these. So the first one, we have 80 decibels. So 12 minus 4 gives me that 8. So 10 to the minus 4 watts per meter squared, 80 decibels. That's one quick one we might be able to do in our head. If not, we can plug it in here and we'll still get 80 decibels. So beta, or the decibel level, equals 10 log I over 10 to the minus 12. That's our formula for this. The next one, we have 3.6 times 10 to the minus 10. I know that 12 minus 10 is 2, so I should end up with something in the 20 decibel range. But I plug that into my equation and I get 25.5. 27 decibels. 27 divided by 10. 10 to the 2.7, 10 to the log gets rid of that. And then we do 10 to the minus 12. Also, remember, if I have 27 decibels, I can just do 10 to the 2.7 times 10 to the minus 12. And that will also give me my answer, which ends up being 5 times 10 to the minus 10 watts per meter squared. 32 is a string problem. We're increasing the tension from 90 to 95. My equation is this. I plug in frequency 1, I adjust the tension, and I get frequency 2 to be slightly higher at 448.97. Remember, tension is the only thing that goes up as frequency goes up. Everything is an inverse relationship, everything else. So length, diameter, and density. Number 33 talks about the frets on a guitar. If I take a string that's this long and I want to double the frequency, I need to touch the string in the middle, and I end up cutting off this much. To double the frequency again, I have to cut the string in half again, so I cut off this much, which means I didn't cut off nearly as much, but I did cut off 50%. So the percentage stays the same that I cut off, but the frets can't be as far apart, otherwise I would end up doing more than changing double the frequency or whatever. 34, this time we're changing a string twice. We're adjusting the length by maybe holding a fret on the guitar, and we adjust the tension somehow. So frequency 1 is 280 divided by frequency 2, length 2 over length 1, and the square root of tension 1 over tension 2. I chose tension 1 to be 1 because I'm supposed to double it. So for tension 1, tension 2. So I'm going to do 280 times 85 divided by 70 divided by the square root of 1/2, and I get a frequency of 480.8 hertz. Number 35. 35, we have a closed tube 30 centimeters long. It resonates at its shortest resonant length with a tuning fork. The air is 25 degrees. So a few things there I noted. If it's the lowest, or the fundamental frequency, it's holding a fourth. So 1/4 of a wave is 30. That means the whole wave is 120, or 1.2 meters. Velocity is frequency times wavelength, but we need the velocity, so 331 plus 0.6 times 25, we've done that multiple times on this review, equals the frequency times the wavelength, which is 1.2, and we get 288.3 hertz. Moving on, making pretty good time here. Hopefully you understand what we're doing. 36, how many times louder is this 60 decibel sound than a 20 decibel sound? So that's up here. That's a difference of 40 decibels. Every 10 decibels is 10 times louder. So that means 10 times 10 times 10 times 10. That gives us a 1 with 4 zeros after it, or 10,000 times louder. If it was 60 decibels louder, that would be a 1 with 6 zeros after it. So that would be 1,000,000 times louder. If it is 20 decibels higher, that's a 100 times louder, because that's a 1 with 2 zeros. 37. Length of an open air column that resonates at its first resonant length with a frequency of 560, speed of sound 350. So I do 350 divided by 560, and I get a wavelength of 0.625. That's not going to change. The wavelength is what it is. But we're supposed to have the fundamental frequency of an open tube. An open tube holds half of a wavelength. So whatever the wavelength is, I need to divide by 2 to get the length of the tube. And I'll remind you with a picture that looks something like that. Okay, so the whole wavelength does not fit in this tube, only half. So that's from crest to trough. So we can see the half a wavelength, and I've just mirrored it there because it's resonating. 38, we have another Doppler effect problem. This time a jet is traveling towards you at half the speed of sound. So I decided to work in Mach numbers, not 340. But the source is moving, so we have velocity of sound over velocity of sound plus or minus the velocity of the source. I chose a frequency of 1 because it's very easy to see what happens to 1 is equal to Mach 1 divided by Mach 1 minus 0.5 Mach. So that's 1 over a half. That ends up being 2 times. 39, another Doppler effect problem. This time the observer's moving, and we are moving, let's see, where is this problem? 39. You're traveling towards it. So if it's towards, it should be higher. So I do 344.8 based upon the 23-degree temperature day plus 25 meters per second divided by the 344.8. Solve that all out and multiply it by 280. I get 300.3 hertz. Number 40. Refraction of sound. Simple. Sound travels slower in cold air, so it bends towards colder air. That's what it does. That has some odd phenomenons in that it bends away from hot parking lots, or it bends towards cold lakes and bounces around and travels across the smooth lake surface. So you can hear sometimes over ice or over cold lakes. I can hear sound over incredible distances. Number 41, I have 2 tuning forks. When they're struck together, I count 18 beats in 6 seconds. That's 18 cycles per 6 seconds, or 3 hertz. If it's a 256 hertz fork, I'm simply going to add and subtract 3 hertz to get the other possible frequency. So 253 or 259, either one of those subtracted from 256 gives us, with absolute values, 3 hertz. Moving along, we are now at 22 minutes. So number 42. 42, probably one of the trickier ones on here for people to think about. Just trying to figure out what we're asking for. So I'm going to actually read this one. How long must a closed tube be in order to hold the first and third resonant lengths? Those can't be the same tube. They have to be different tubes. So we'll address the first resonant length first. First resonant length holds 1/4 of a wave. Well, we need to know what the wave is. So I know that 3/4 of the wave happens to be 24 centimeters because the second resonant length of a tube that will hold this wave is 24 centimeters. So 3/4 of a wave is 24 centimeters. That means the whole wave is 32. I'm working in fourths of a wave, so I went and figured out that 1/4 of a wave happens to be 8 centimeters. So 1/4 of a wave is 8 centimeters. That's the answer to the first part. The third resonant length is 5/4 of a wave, so 5 times this gives me 40 centimeters, or 5/4 of 32 is 40. So a tube that's 8 centimeters long will hold it. A tube that's 24 centimeters long would hold it. And a tube that is 40 centimeters long would hold it as well. It's most happy playing in this tube, but it would resonate in all 3 of those tubes. Number 43, what's the lowest frequency that will resonate in a 2-meter long closed organ pipe? Well, I know it's 2 meters long, and that's holding 1/4 of the wave, so the wavelength is 8 meters. Velocity is frequency times wavelength. So 340, I chose that because that's the speed of sound we gave you, and we don't have another speed of sound or a temperature, is equal to frequency times 8. Frequency is 42.5. That's an octave above the lowest note that humans can hear, right? About 40 hertz is about an octave up. So that's a very, very low note. Gives us some cool bassy stuff. 44 gives us 4 tuning forks. It's kind of a confusing picture here, but I've explained what we've got. We've got 446, 440, 443, and 449. Beat frequency is simply frequency 1 minus frequency 2. So I just subtracted each one of these. I did 440 compared to 446 gives me 6 hertz difference. 440 to 443, 3 hertz. 443 again to 449 is 6. 440 to 449 is a whole 9 hertz. And I wrote down 6 hertz there. That was supposed to be 9 hertz. It's amazing what you can catch when you're going through this. 443 compared to 440 is 3. 446 to 449 is 3. So subtracting any combo of those numbers, I get 3, 6, and 9 hertz. Last one, 45. We've already kind of discussed this one a moment ago, but sound refracts towards cold air, so it can really change the direction sound is coming from. If you have warm and cold air, it becomes a little bit weirdly directional. All right, I hope that's been helpful. I hope it's been able to get you all that you need.